So we're going to look at truth tables. So, of course, P and Q represent statements which can be true or false. And then we have a disjunction, P or Q. And can somebody say when P and can somebody maybe articulate when P or Q is true?
They're both true. P or Q is true when either have, trying to word it, it's only false when both are false.
That's right. That's a good way. So you can say that it's true, that the disjunction is true when at least one of the two proposition is true. As soon as one of them is, right? Both of them could be. One of them could be. All right. So in a truth table, we have all the possible truth value combinations of the truth values for the two propositions, P and Q. And then we see that P or Q is true as soon as one of them is true. So as soon as you see a true statement there, we know it's true. The only time it would be false is if both propositions are false. So we see that in the first column, we're negating that statement. So not true means false, not true, false, and so on. Okay, so the next column is a conjunction, right? We have P and Q. So that we know conjunctions are true only when both of the propositions are true. So here we have, well, let's negate P. So not P, not P, not F, I mean not P and not P. Then we have Q. So then the conjunction is going to be true only when both propositions are true, false otherwise. Okay. So here it's true if at least one proposition is true. And conjunction is true only with both propositions are true. Okay, so then let's take these, let's see, this says it's an implication, I see. This is the antecedent, and this is the consequence. So here we have for the antecedent, we have a column, so we see that it's going to be false, 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 true. So I'm just copying down one of the columns, and then I'm going to copy down the truth values of the antecedent, which we have instructed here. So false, false, true, and false. Okay, and then the implication, let's just use different letters. No, let's use P implies Q. We know that the implication is only, well, it's true oops, I wrote that twice. Okay, so the only time the implication is false is if the antecedent, the P, is true, but the consequent is false. Otherwise, it's true. Okay. So over here, we see that the only time this is the only time that this is false is if truth implies falsehood, right? Otherwise, the statement is true. Okay. And of course, the instead of here in the last column, we reversed the antecedent, the consequent, right? So we have the converse of the preceding column. Well, again, we'll just write down the truth values of the antecedent, not P and Q, which we have conveniently in one of the columns. And the consequent, there we have the green column. You can write down the truth values as well. So we see finally that the only time implication is false if truth implies falsehood. So this is false. Otherwise, it's true. Okay. Any issues with constructing truth tables?
No, I think I'm okay with truth tables.
Okay. Does anybody have questions about the truth table, say on your review, or anything serious? All right. Okay. In that case, we can move on to number 2. All right. So number 2, we just want to practice negating statements. Okay. And this involves here quantifiers. So there's the existential quantifier. Sometimes we use the symbol like that. I don't know if that's what you learned in class, but this denotes the statement there exists, there is a, or some. And then you have the universal quantifier. For all, so all or for all things, right? All right, and so let's try to negate the statement, some unicorns live in apartments. Anybody want to volunteer? Okay. Well, if we claim that some unicorns live in apartments and somebody thinks it's false, we would say that no, all unicorns do not live in apartments, right? Or you could probably better English would be no unicorn lives in an apartment. So the opposite of some unicorns having a property is that no unicorns have the property. So you can say the negation is all unicorns live in some place which is not an apartment. better English probably would be that no unicorns live in an apartment. Okay, so when we say that for the next statement, which says no unicorn wears a tutu. Okay, so that's the same thing as saying all unicorns do not wear tutu. Right, that's equivalent. So the negation of that would be that, well, some unicorns, there exists at least one unicorn that wears a tutu. Okay, or maybe shorter, some unicorns wear tutus. Okay. All right. So finally we have, I think it's fine. No, it's not. We have all people who wear a tutu are ballerinas. So this is a statement with a universal quantifier. All people who wear a tutu are ballerinas. So the negation would make us switch that out for a existential quantifier, right? So there are some people who wear a tutu. So some people wear tutus and are not ballerinas, or you can use the word but equivalently, right? But and have the same logical function. It's a conjunction. Some people wear tutus but are not ballerinas. Oops, I misspelled ballerinas. So here we could have make this maybe clear by realizing that this is a implication, right? It says that if a person wears a tutu, then they are a ballerina. So if let me just say, so if a person wears a tutu, then they are a ballerina. And so if you want to negate an implication, this would be not Q and P. Or if you'd like, P and not Q. So here we're saying if a person wears a tutu, they are a ballerina. The negation of that could be that there's a person, right? And there's a person who wears a tutu and they're not a ballerina. Okay. So then we have some tropes are often true. Again, some is a existential quantifier. Negating the statement turns that into a universal quantifier. So we can say all tropes are, and then we negate the statement. So let's say always false. Okay, so does anybody have questions about recognizing universal quantifiers, all for every, and existential quantifiers like for some, and then negating those? Oh, why wouldn't the negation of no unicorn wears a tutu? Okay, that's a good question. Let's go back to that. No unicorn wears a tutu. Well, they're saying that, so no unicorn wears a tutu. That means that there's no unicorn in the universe that you'll see a tutu on, right? So the opposite of that is that there must be a unicorn that is wearing a tutu somewhere. No unicorn wears a tutu is the same thing as if something wears a tutu, then it cannot be. It's not a unicorn. So the negation of that would be that so there's something that wears a tutu and it is a unicorn, right? So there's a unicorn that wears the tutu. All right. All right. So we negated some statements, and now we're gonna take symbols and turn them into words. Okay. So we have two propositions. P is San Antonio is a great city, and Q is Dallas is nice. So we're supposed to then, looking at symbols, be able to do things like articulate not Q, right? So not Q. So it's just saying this Dallas is not nice. Okay. And then P and not Q. So this is should be pretty straightforward, right? Because you just say P is San Antonio is a great city. And so you have the conjunction that we use the word and for that. And it's not the case that San Antonio is a great city. So not Q. So and Dallas is not nice. All right, and then the last one is there really just to maybe review De Morgan's laws. So let's look at De Morgan's laws. Because I could say it's not the case that San Antonio is a great city and Dallas is not nice, but that's kind of weird. So we probably want to use De Morgan's laws first for logic here. So that De Morgan's tells you what to do when you're negating a conjunction. So not A and B is the same as not A or not B, right? So as soon as one of those statements is false, the whole conjunction is false. So we kind of distribute the negation, but we make sure to flip the wedge into a V, right? And vice versa. De Morgan's laws also work for negating a disjunction. So not A or B. Again, you distribute the negation, so to speak, and you flip the V into a wedge. So this is what you want to do first, probably before articulating this into words. So not P or not Q. So let's remind ourselves that double negating just gives you the original. So not P or Q. So since P is San Antonio is a great city, not P is San Antonio is not a great city. And here we had and originally, but because of De Morgan's laws, we traded that in for a or. So or Q, so or Dallas is nice. Okay. And so you can imagine that if you're supposed to translate symbols into words, there should be a problem, right, where you're translating words into symbols as well. So we're going to translate into symbols. So where it is raining is going to be represented by P, and I bring an umbrella is represented by Q. All right, so the first statement, it is raining and I didn't bring an umbrella. Well, this is represented by P, and is a wedge, it's a conjunction, and then we have a negation of I brought an umbrella, right? I didn't bring an umbrella, so it's the negation of the statement that I brought an umbrella. So that's a negation. Okay. And the next sentence is, it is raining. So that's represented by proposition P, or is a disjunction or a V. And again, I didn't bring an umbrella as a negation of statement Q. All right, so then we recognize the typical, probably the most common way to write out an implication. If the antecedent, then the consequent. So if it is raining, then I bring my umbrella. So if P implies Q. The if then, if P then Q is written as P implies Q. Okay, now we have another if then statement. So it's another implication. But the antecedent this time is I didn't bring an umbrella, which is the negation of not Q, which is the negation not Q. And then the consequent here is that it is not raining, so that's the negation of the statement that it is raining, so not P. Okay, and what's the, if P implies Q, that's the implication, then what do we call not Q implies not P, just as a review? This is the something of that. So P implies Q, and then if you negate and then switch the antecedent with the consequent, so not Q implies not P, there's a name for that we need to know. Okay, so we call that the contrapositive of the implication. Okay, and they're in fact equivalent. If you look at the truth table for an implication and contrapositive, they're exactly the same. They're equivalent logically. They're equivalent logically. All right. So the next statement is, it is raining only if I bring an umbrella. So the P only if Q part, that's not as common because it's difficult to understand. Honestly, it's another way of writing implication. P. So this is the antecedent and this is the consequent. Even though it's confusing because you typically what follows the word if is the antecedent, but this time it's the yeah, I don't quite understand why people would use that. It just confuses everybody. But I saw it on your review, so I would mention that. The P only if Q is really P implies Q. Okay. So the last one is, it is not raining or I bring an umbrella. So that's, I don't know. That's negation of P or, and then I bring an umbrella as Q. That's probably also equivalent to an implication. They would have the same truth values. All right. Do you want to, any other, maybe from the review, any other phrasings which you find not clear? If you want that we need to translate into symbols? All right. In which case, oh yeah, so let's just talk about an implication here. And so this is just reviewing some terminology. So this is an implication. P implies Q. And we already talked about the contrapositive. So contrapositive is equivalent to the implication. It's just we negate the antecedent, make it a consequent, and negate the yeah. So P implies Q is the same thing as not Q implies not P. So if it rains, I bring an umbrella is equivalent to I don't have an umbrella. Oh, sorry. If it rains, I bring an umbrella is equivalent to if I don't have an umbrella, that implies that it's not raining. That makes logical sense. Now the converse is just where if you have P implies Q, the converse is that Q would imply P, right? But these are not equivalent. We know that if P implies Q, that does not mean that Q must imply P. And then the inverse. So this is where we just negate the antecedent and the consequent, but keep not P implies not Q. And again, this is not logically equivalent. It's not it doesn't have the same truth value as the implication. But the inverse is logically equivalent to the converse is logically equivalent to the inverse, just like the contrapositive is logically equivalent to the implication. All right. So we make sure we know those definitions. Okay. So I guess next we need to work with integers in different various bases, right? Okay. So if we're given a number in decimal and we need to convert to a different base system, let's say binary for now, we would have to, I'm assuming you're allowed a calculator. So since we're converting to binary, we should look at just maybe list all the powers of 2 that we can quickly generate. And how high do we need to get here? When should I stop listing these? Oops, I forgot 3. My bad. Well, we can probably stop listing these as soon as we see something bigger than our number and decimal. So not yet, but 2 to the 9 is 512, right? So we see that's bigger than our number 345. Okay. So then we would say, well, how many times? Well, we see that this will go into 345, right? So how many times? Just once. So we see that 2 to the 8 goes into 345 decimal once. Okay, so we know that for our binary, we have that 256 goes into 345 once. So we're going to have, for the 2 to the 8, we're going to have a coefficient of 1 to indicate that 256 goes into 345 once. Okay, so then we can update our number because we already accounted for 256. So we subtract 256, and we get where's my calculator? Because I don't. Let's see, 346. Okay. So we have 90 left over. Okay, so now we look for so 2 to the 7. Does 128 go into 90? No. Right, so we see if 128 goes into 90. It doesn't. So this means that we don't have any 2 to the 7th terms, so 0, to indicate that 128 does not go into 90. Okay, does 64 go into 90? Yes. And it goes into 90 once. So we're going to have a +1, 2 to the 6. And that's 64. So now we update our number. 90 minus the 64 we just took care of. So that gives you 26, I guess. So. Okay, so then we look at 26 and we ask ourselves, does 32 go in there? No. So that we know that there are no 2 to the 5 terms. But 16 does go into 20 exactly once. So 16 goes into 20 once, right? So we'll go ahead and indicate that by saying let's add one of those. Let's update our number. That's 4. And then we see that 8 does not go into 4. So 0. But 4 does go into 4, and that goes in there once. Okay, and so then we update our number. 4 minus 4 is 0, so we're done. So the rest of the factor, we have no other powers of 2 included because we have counted for all our whole number. And then the binary expression is just the digits multiplying the consecutive powers of 2. So our number in binary is going to be 1, 0, 2. Oops, that was bad. It's not a 2. There's no 2. Binary only has 0 and 1 digit. So 1, 0, 1, 0, 1, 0, 0. Okay. Okay, and this idea can be expanded to, I guess, any base. So we can do 345 in decimal and convert it to, let's say, a number in base, I don't know, 7. Right, so towards that end, I would probably list some powers of 7 on my calculator quickly until I get something larger than my decimal number. Well, I guess I should have been prepared. I don't know 7 cubed. 343. Not quite, right? But 7 to the 4 is definitely going to be bigger than our number. So we don't even have to list it. All right, but there we go. We have, we see that 343 goes into our number exactly once. So let's, we'll have 7 to the 3, 7 squared, 7 to the power 1, 7 to the power 0, just a constant. So 743 goes into our number once. So we'll indicate that by putting a 1 there. All right, and let's update our number. Well, this was cheesy. I didn't really plan on this number working out this way. That's a 2. So 49 does not go into 2. Neither does 7. But then 1 goes into 2 twice. So we'll indicate that like so. Anyway, so in base 7, our number would be 1002 in base 7. Is there any particular base you want to see?
Not a particular base. I just got confused with the 7 to the power of the 0. Why is it 2 again? Like for the final digit, why is it 2?
Right, so we see that 343 went into 345 once, and then so we updated our number by subtracting, and then we saw that the other powers of 7 don't go into 2. 49 doesn't, 7 doesn't, but 1 does. And how many times does 1 go into 2?
Oh, okay, gotcha. I forgot that you use 1 as that power. Okay, that makes sense.
Yeah.
Thank you.
Sure. All right. All right, so if we need to turn decimal into the same number in other bases, of course, we're going to have a related problem in turning an integer into a non-standard, non-decimal base into decimal. And which one's easier, do you think? Turning decimal into non-decimal or non-decimal to decimal? Well, I'm thinking turning non-decimal integers into decimal is easier, right? Because you just write this out. This is consecutive power base 7. So we have consecutive powers of 7. So 7 to the 0 or 1, 7, 1, 7 squared, 7 cubed. So that's the 0th place, I guess. First, second, third. So up to power 4. Okay. And then we have the coefficients. 5 is multiplying 7 to the power 4. 3 plus 0 plus 4. Right, and then it's just calculator work. So we would have, so this is, let me just write it out. So that's 5 times 2,401, 343. So 3 times 343, 0 times 49, and then 1 times 7, and then 4 times 1. So whatever that turns out to be. So I think turning non-decimal to decimal is a little easier because you can just, you have the coefficients multiplying the consecutive powers of whatever the base is. Okay. All right, so now we're gonna, we want to add numbers and bases other than base 10. So I guess what are the rules? If you get something that's, if you add digits and you get something that's the base or higher in value, then you just subtract the base to see what you get. So for example, this is base 4. And so when I add 3 and 1, I get 4. Okay, so I get 4, but I wouldn't write that because the only digits you would see in base 4 are 0, 1, 2, and 3. So if he gets 4 or something higher, we just subtract that from 4. Okay, and so 4 minus 4 is 0, and that's what we get over here. And then we carry 1. Okay, so then we have 1 plus 1 plus 1 is 3, and that's less than our base, so we're good. Okay, then we have 3 plus 3 is 6 in decimal, right? But since that's bigger than our base, we subtract the base value from that 6, and that's what we put over here, 2. And then we carry 1. Okay, and finally, we have 1 plus 2 plus 1, which is 4. So we would, that's our base value, so we subtract the base value, and then we put a 0 here and carry 1 to the next column, I guess, and then we add 1. There you go. Do you want to try another one that's like a different base? We can talk about hexadecimal in a second, but I can give you some time to. Okay, so try adding these two numbers in base 5. I'll let you post your answers in chat. I'll wait a couple minutes. I'll start going over this as soon as I see an answer. Oh. Okay, let's look. Let's look at Dan's answer. So that's 100215 and base 5. Let's see. Okay, so 4 plus 2 is 6, which is at least the value of our base. So we take 6 and we subtract the base value to get 1, and that's what you put over here. And we carry 1. Okay, then in the next column we have 1 plus 1 is 2. That's less than our base value, so we can just put that down. And then we have next column is 2 plus 3, which is 5. That is about our base value, so we subtract the base value to get what we have to put down, and we carry 1. And then 1 plus 4 is 5. That is our base value, so subtract the base value and carry 1. So very good. 10021. Okay. Yeah, without the yeah. I see. All right. All right. So what is what's the base value for hexadecimal? So let's look at hexadecimal. Yep. All right. So for hexadecimal, most of your computer scientists, you probably need to write down that the digits are the base is 16, right? So hexadecimal, hex is 6, decimal is 10, so 6 plus 10 is 16. So the digits would be 0 through 15. Except we don't want to write 10 because that uses 2 digits, so we just call that A. So that's 10. B, 11. C is 12. D is 13. Finally, F is 15. Okay. All right. So let's see. If we have, let's write this down, B2EC plus F38. All right, so when we see C plus 8, we have to translate the C into a 12, right? So C is 12, and then we have plus 8. So that would be 20. And 20 we see is larger than our base value, or it's at least as large, right? So we take that 20 and we subtract the base value to get 4. And that tells me what digit to put over here, and then we carry 1. All right. So for the second column, we have 1 plus E plus 3, and we just translate E into, we know that it represents a digit, quote unquote, that represents the number 14. So we have 15, 18. And 18 is larger than our base value, so we subtract the base value to get 2. And we carry 1. All right, third column. 1 plus 2 plus F is 1 plus 2 plus F is 15. So that's again 18. Not too very exciting, but that's greater or equal to our base value. So subtract it to see what digit goes here, and then carry 1. And then 1 plus B is the same as 1 plus 11, so that's 12. But of course, in hexadecimal, 12 is represented by the digit C. You want to try another hexadecimal one, or do you want to go on to subtraction? Okay, I'll let you try a hexadecimal one, and then I'll keep these up. So let's see. Let's try. Let me copy this. And let's try adding 2, 8, 0, C, E, F, and then I guess 1. And these are clearly in hexadecimal because we see letters. So I'll let you add those on your own for a second. I'll go over it as soon as I see an answer in chat. Anybody care to venture an answer? Or are we all completely stumped here? Or is it just too easy to even mention? Okay, well, let's go over it. So we have, for the first column, we have 2 plus 8, which is 10, which is not at least the base value of 16, right? So we don't have to subtract. But, of course, we don't write 10 down. We know that in hexadecimal, 10 is represented by A. So we just get A, and there's no carry. Okay. Then we have 0 plus C is C. I should have done 1 or something, but oh. Then E plus, so 0 plus C is just C. Then third column, E plus F is really 14 plus 15, 29. This is bigger than the base value, so we subtract the base value of 16, and we get that it's 13. Okay, so we would put down the digit representing 13, D, and we carry 1. And then 1 plus 1 is 2, and we're done. All right. Okay, so are there any questions about adding numbers in different bases? Okay. In which case we would want to go on to subtracting numbers in different bases. So I have one in decimal, but I mean, sorry, hexadecimal, but maybe we should start with something else. Let's see. All right, let's subtract in base 3. Why not? So the base 3, the only digits are 0, 1, and 2. So we have 1, 2, 1, 2, whatever, minus 2, 1, 2. Okay, that's cheesy. Never mind. 1, 2, 1, 2, and then 1, 2, 2 or something. Okay, that's better. So this is in base 3, and we're going to subtract. Okay, so 2 minus 2 is 0. That's fine. Now, 1 minus 2 is a negative number, so that means we need to borrow. For the second column, 1 minus 2 is negative. So we're going to borrow from this column, so the 2 becomes a 1. Okay, and when we borrow, we're borrowing the base value. We're borrowing a 3. So then you say, well, 1 if you borrowed a 3 over here, then this would become, I'll put that in different color because it's not the same base, but it's going to be 3 plus 1 or 4. And then we go 4 minus 2 is 2. And then 1 minus 1 is 0, and 1 minus 0 is 1. So let's try that with base 7, I guess. Oops, base 7 would only have digits 0 through 6. So, okay, and this is base 7. So we go 1 minus 6. Okay, that is a negative number. So that means we need to borrow. So from the next column, so this 4 will become a 3. And when we borrow in base 7, we're borrowing a 7. Borrowing, sorry, 7. So we get 7, and then this plus 1, that's 8. And now you can say that 8 minus 6 is 2. Okay, and then 3 minus 4 for the next column is negative. So we need to borrow. So this, we borrow from the next column, so that 6 will be reduced to a 5. And when we borrow, we're borrowing a base value of 7. So, sorry. So we get 7 plus 3 is 10. And then 10 minus 4 is 6. And then finally, 5 minus 0 is 5. Do you want another one? I think subtracting would be the most, seems like the kind of most difficult thing. Oops. Well, let's just try it with decimal, hexadecimal, sorry. Well, come on, move. All right, so let's try this. C minus 8. So for the first column, we would want to think of that as C minus 8 is the same as 12 minus 8. So that's equal to 4. So that's what our digit will be. Okay. Next column is D minus E. So it's 13 minus 14. So that's a negative number, right? So we have to borrow, okay, from the next column, meaning that this 2 will become a 1. And when we borrow, we're borrowing the base value of 16. So we get 16 plus D, where we know D is 13. So this is 19. Okay. So then we can do the subtraction. 19 minus E is 5. E is 14, so this is 5. Right. Next column is 1 minus F. Well, obviously that's going to be negative. So we're going to borrow. So we're going to borrow from the next column. We're borrowing from B, which is 11. So you have to subtract 1 and you get 10, right? Or A if you'd like. And when we borrow the base value of 16. So we get 1 plus 16 is 17. So 17 minus F is the same as 17 minus 15. So we get 2. And then finally, A minus 0 is just A. You want to try one on your own? So let's do, okay. Again, these are hexadecimal. All right, so first column, 7 minus 8. is a negative number. So this means we in fact can't subtract. We need to borrow from next column. While the next column we have an f, sorry. F has value 15. So when we borrow, that becomes 14, or it becomes E. Right? And when we borrow the base value of 16. So 16 plus 7 is, what is that, 23? Okay, and then so we have 23 minus 8 is 15, which in hexadecimal is denoted by digit F. Okay, so second column, we have E minus A. E is 14, A represents 10, so we get 4. That's completely valid. Okay, so then we get A minus 9. A is 10, 9 is 1. Okay, so we get 1. All right, well, do you want to practice subtracting more? Or do you have any questions about anything on this review or your professors? I can go over any sort of problem you'd like. There doesn't seem to be that much material, honestly, or maybe I'm just, I don't know.
Actually, I just had a quick question. Do you know what like the exam? Is it everything that we just covered? Is that like all the material that's gonna be on there, or do you know if there's gonna be other stuff that we didn't cover?
That's a great question, and I do not know the answer. Well, I just
Okay.
got an email from Dr. Sutton out of the blue asking to do a
Okay.
review. I'm like, sure. And this is the only thing she provided was the review that you'll probably given.
Right. Okay.
Yeah.
Thank you.
All right. I guess it's your last chance to ask any question or ask about any type of problem. I can make an example for maybe. Well, okay then. I'll go ahead and I guess get this edited really quick and post it on YouTube, and then hopefully in an hour or so. If you don't have any other questions. Okay. Well, thank you for joining me this Sunday, and I hope the exam goes well. All right. Thank you.